Hello students, so today we'll discuss about two important aspects of physical vapor deposition. We'll take up evaporation and sputtering. These are the two important means by which physical vapor deposition is done in thin films. Now, first we'll start with evaporation. Evaporation, as we all know, is a process of evolution of vapor from a solid surface by means of Joule's heating, and the evaporation is mainly done in a vacuum environment so that the film is free of contaminants. Now, the rate of evaporation, the rate of is not limited by the insufficient heat supply. Although we are using a Joule heating, so there is a condition that it is not that the more heat is applied, the more evaporation will take place. Insufficient heat is not related to rate. It is in fact related to the vapor pressure. And the rate is proportional to the difference between the equilibrium pressure, as I just said, that is equilibrium pressure of mercury, and the hydrostatic pressure acting on the evaporator, that is P minus Pg. And similarly, the maximum rate we obtain with the number of vapor molecules emitted corresponds to that required to exert the equilibrium vapor pressure, with none of them returning. So based upon that, the rate of evaporation from both liquid and solid surfaces, this is the equation for the rate of evaporation, and this phi E is actually the evaporation flux, that is the number of atoms or molecules per unit area per unit time that has been evaporated, and it is equal to alpha E, which is the coefficient of evaporation. That is lies between 0 and 1. Avogadro's number, the pressure difference, into 2 pi mRT, mass of the evaporant, is the gas constant, is the temperature. Now, when this gas evaporant coefficient alpha is equal to 1 and pH is equal to 0, then only we will get the maximum evaporation rate. So when pH is equal to 0, that means this condition is satisfied. Now, there are 5 ways by which we can provide the Joule heating. One is a resistive, inductive, using electron beam, using an arc, and using a laser. The resistive is we use a wire of refractory metal, for example, tungsten, and the shape of the wire is like this. And or we can use a boat like substance. Inside we put the evaporant, and this boat is made up of the following insulating materials: alumina, and beryllium oxide, boron nitride, KiB2NBN. Second is inductive, where we are using refractory oxide and nitride crucibles, as in this case. And the disadvantage associated with inductive is it has got bulky RF coils. We can use also electron beam, high energetic electron beam directly onto the evaporant to cause evaporation. We can use a cathodic, or we can use a laser. Now, as we have said, the maximum evaporation rate is calculated when pH is equal to 0 and alpha is equal to 1. It comes around 3.5. This is the amount, and that P is expressed in torr. Whereas the mass evaporation rate is this amount, root m by T into P. So at 10 to the power minus 2 torr, this is the mass evaporation rate that we obtain. And the key variant influencing the evaporation rate is, of course, the temperature, which has profound effect on the equilibrium vapor pressure. Next PVD technique is sputtering. Sputtering is basically a process of ejection of atoms from the target by means of momentum transfer, and the momentum transfer takes place from the ions, energetic ions produced in the plasma, which are accelerated to the target by means of electric field. Now the cathode, the target, or this also called the cathode, is negatively biased, and it is water cooled from the outside, and this whole thing is inside a chamber, inside the vacuum chamber, and we maintain a vacuum. The vacuum is required for to remove the contamination. Also, there is a term called the Newton number, or it's also called Kn, which is equal to lambda by L. Lambda is the mean free path, and L is this distance. This is your L. Lambda is the mean free path. So by keeping lambda by L greater than 1, that means keeping the mean free path more than the value of this distance. It means that lambda means that the distance traveled between two collisions. So this means that the collision is avoided. So we can actually cause the atom which are produced to directly fall onto the target before suffering any collision. And this momentum transfer is actually a little different process. The argon atoms don't strike it perpendicularly, they strike it at an angle, and by a collision cascade, that means from this momentum is transferred to this atom, then to this atom, then to this atom, and then eventually the atom gets ejected out of the target and gets deposited onto the substrate. Now when an ion is incident on a target, there are few possible things. It can bounce back, it can get implanted, it can get absorbed, or it can cause reflection by grazing collision sequence. This is what sputtering is all about, grazing incident. So we can very well understand that if the atom, if had it been the argon atom, had it been struck in perpendicular direction, there would have been no ejection of atoms, because this glazing and this reflection of atoms wouldn't have taken place. That is why it is always preferred to use a grazing collision. So it has been found that the maximum efficiency can be obtained if we eject the atom at 60 degrees. We get the best sputtering possible. Now this sputtering is used in the aluminum and copper based interconnects, and if you compare it with evaporation, so it gives you better uniformity, and we have better control of the composition, and we can do a pre-surface cleaning before the film position takes place. So these are advantages of sputtering compared to evaporation. Now, as we have said, that a lot of possibilities are there when an ion is bombarding on a target. Now we have to take care of mainly these two possibilities. That means either we want the ion to get implanted, or we want the atom to get knocked off. So based upon that, we have a threshold energy, that is the minimum energy for sputtering, and it depends, that is the minimum energy required for the atom to get knocked out of the target, and it depends on the ratio of the mass of the target and the ion. So it is proportional to mass of the ion by mass of the target to the power 2 by 5. And talking about the different energy ranges, so if the energy is low, less than 5 electron volt, then resorption or reflection may take place. If the energy is between 5 to 10 electron volt, then the surface damage and surface migration may take place. If it is 10 to 30 electron volt, this is the energy range that we should keep while doing a sputtering. So if it is 10 to 30 electron volt only, then the sputtering will take place. And if it is more than 10 electron volt, then ion implantation will take place. So you can see that there is an overlapping, and this overlapping is actually again dependent upon a lot of things: sputtering, yield, angle, pressure, etc. So the transfer of energy it can be expressed again is depending upon the mass of the ion and the mass of the target and energy of the incident ion. This gives you the energy transfer, and is equal to, and this quantity this quantity is represented as phi m into E, gamma m into E. Now there are a few parameters on which sputtering is based, like the sputtering yield, that means the number of sputtered atoms per incident ion. Sputtering yield can be 1, can be even 2, and it can be even a fraction. That means 1.5. That means for two ions, suppose this 3 atoms are coming out, so the sputtering is 1.5. Is it 1, 2, 3, maximum 3, and maximum 3 can take place. It's very unlikely to be more than 3 and 4. Next is your sputtering rate. That means how the sputtering takes place from the target, and sputtering rate is actually sputtering velocity. That means the velocity with which the atoms are coming out per time, and so it is expressed by this expression m by R n E into SAP. M is the molar weight of the target, expressed in kg per mole. R is the density of the material expressed in kg per meter cube. N is the Avogadro's number. S is the sputtering, and Jp is the current density. So let's take an example for a target of tungsten. If we are having the following values: 184 grams per mole as the molar weight, 19.26 grams per centimeter cube as the density, sputtering yield 1, that means 1 tungsten atom per incident ion, and 1 milliampere per centimeter square is the current density. Then the sputter rate comes to 25 nanometer per minute. Now we can express this sputter rate in terms of monolayers. So if there is one single atom deposited on a substrate, so the monolayer will be 2 into the radius. So that is why we are expressed the sputter rate as 2.62 monolayers per second. So this the sputtering, there are some limitations of sputtering. That means the normal sputtering. That means for a sufficient deposition rate, you require some high pressure. By high pressure we mean a required medium vacuum. The vacuum is less than the vacuum required for evaporation. So this can cause impurity. So what we require is we need to enhance the sputter rate or deposition rate without changing the vacuum, without loading the vacuum very much, or without increasing the pressure. So for that there are 2 ways we can do it. Either we can do it by something called the bias sputtering, or by a magnetron sputtering. Bias sputtering is nothing but you give a small negative bias to the substrate, so that the ions can come and clean the substrate, and also it can be also applicable for the target as well. So before sputtering is taking place, ions are coming and cleaning the substrate, and this is one of the methods. So we did not play with we did not load the vacuum in this case. And the second method is called magnetron sputtering. Now magnetron is a device where the magnets are placed in a circular fashion so that we get a crossed electric and magnetic field generation. So this magnetron is actually placed just of the target, and so due to this E cross B field, there is confinement of secondary electrons, or the charges gets confined just below the target, or we can say in the line of sight. So this is the line of sight, this is the substrate. That is why the sputtering efficiency increases. Okay. And so now there are 2 ways by which we can do the magnetron sputtering. Either we can do it with DC magnetron sputtering, which is for conductors, and we can use the AC magnetron sputtering or radio frequency magnetron sputtering. In the case of DC magnetron sputtering, we need to keep the cathode at the constant negative value, and the ions are coming and hitting the target. So So this is good for conductors. But however, if you're using an insulator, so the ions may come and neutralize the negative bias substrate, and also when there is, so for that we require something by which the neutralization is not taking place. So that is why we use an RF. Now one can say that if RF means there will be a change in polarity from cathode to anode, that means the target will be either negatively charged in the first cycle and it is positive charge in the second cycle. So whatever atoms sputtered, so this is the target, say. So this is the target, and it's a different color. So if this is the target and this is the substrate. In the first cycle, this is negative, this is positively charged. Argon atoms coming and depositing film. Here in the second cycle, it becomes positive and this becomes negative. So ions will come and hit the substrate. So a negative sputtering will take place. Now this doesn't happen in case of RF. That is the reason, because ions are too massive. When we are applying a magnetic and the radio frequency to the system, that is frequently changing. So since electrons are very lightweight compared to ions, so even if we are changing the polarity, ions are too massive to respond to that change. So it's more often that electrons are getting deposited onto the cathode, or electrons are getting striking the cathode compared to the ions. So we get a self-induced negative bias, and this is the voltage versus time. So this is what is the self-induced negative bias with cycles. A negative bias is established at the cathode. So even if we are using an insulator, and even if we are using a radio frequency, so that will not hamper or that will not cause any negative sputtering to take place.